All right, mathematicians, we are now on to the last section of chapter 5. So section 5.6, which is on the definite integral substitution. We just reviewed u sub with indefinite integrals. So now we're doing it with definite integrals and the area between curves. So this one chapter kind of has two different, main ideas going through it. So it will be a little lengthier of one, but we will get through it. Super easy. So when we were working on 5.5 and talking about u substitution, we didn't have to do too much after finding u and du. We just had to integrate from there and then plug x back in. Well, now I have a definite integral. So now I have bounds on my integral. So it kind of leaves me with two different ways. I can take the bounds off of my integral, so make my definite integral an indefinite integral, find the appropriate antiderivative, and then use the fundamental theorem of calculus part 2. So what that means is, and it'll be clear when we go work through a problem, is I can take the bounds off my integral, change my x's into u's or whatever independent variable into u's, integrate, find my antiderivative with x's, right? So we plug in the x, and then I can plug in those bounds using f of b minus f of a, the fundamental theorem of calculus, part 2. Or method 2, which is my favorite method, is to keep the bounds on the integral and change them to values of u. So if I give you an integral, like this one below, it's going to look like things with x's in it. Those are going to be x equals 2, x equals 1, something like that. Now we're going to change them depending on what we choose u to be into different u values by plugging in x into u. And we're going to evaluate it like normal. So each method has its own, basically its own benefit. Doing the first one, I'll get the antiderivative back out in x's so I can check and take the derivative and see if I get what's inside my integral again before plugging in the values. And 2 is a lot faster. So once you're a little bit more confident and taking the antiderivative, it's really easy to do method 2 because it's a lot quicker. All right, so enough talking about the idea of it. Method 2 also yields this theorem, theorem 5.61. So if g prime is a continuous function on the interval a, b, and f is continuous on the range of g of x equal to u, so basically we're back to u substitution, then the integral from a to b of f of g of x times g prime of x, we can rewrite it as g of a to g of b of f of u du. Because remember, if g of x equals u, g prime x dx equals du. All right, you can think of like a and b are x values, where g of a and gb are u values. Basically, I like to think of this as like going from x to u. Choosing your u is kind of like choosing a language to translate. I'm changing a and b into, I don't know any other languages, into another language. So I'm giving someone directions. I'm like, hey, you need to go from the library, biblioteca, yes, I know that one, to, only other word I know, to the house, to your casa, right? Instead of writing library to house, I'm writing biblioteca to casa. Something like that. If those are really not good words in that language, I'm really sorry. Okay, so let's do an example. Method 1, we're taking off the bounds. They'll be back later and can't forget about them, but I'm just gonna take them off for now, all right? So I'm just working with the indefinite integral, right? So the original integral is from -1 to 1, 3x squared times the square root of x cubed plus 1 dx. So I took my bounds off, so now I just have the indefinite integral of 3x squared times x cubed plus 1 square root of that times dx, right? So pause here if you want to think about what your u should be. And I'm going to choose my u to be x cubed plus 1, making du 3x squared dx. That makes this integral the square root of u times du. Right? Du is right here, and the inside of the square root is u. Alright, cool. I can also rewrite this as the integral of u to the 1/2 du. I like to write it like that just to help me with the antiderivative. And so then I'm going to take the antiderivative. We're going to integrate, and I'll get u to the 1/2 plus 1 is 3/2. I'm going to multiply by the reciprocal, so times 2/3. And I'm not going to add a plus c because I know that I'm going to add my bounds on later, and those will just cancel out. All right, so we plugged in our u's and integrated. Now I don't need u anymore. The whole point of u was to integrate. Now I'm done integrating. And I'm going to plug in u. So, plug in x cubed plus 1 into u. So I'm going to have x cubed plus 1 to the 3/2 times 2/3. And now I'm going to take this and I'm going to do f of b minus f of a. Ooh, big F. You can add your plus c here if you want to be correct, but just know when we do f of b minus f of a, that will cancel out. So in b, in this case, is what, 1? And a is -1. So we're going to do 1 cubed is 1 plus 1 is 2 to the 3/2 times 2/3 minus -1 plus 1. -1 cubed is -1. Plus 1 is 0, so that's just going to be 0. So this is going to equal 2 cubed is 8. So we're going to have 2/3 times a square root of 8. Is that right? Which I think we can then write 2 times 2 times square root of 2 over 3, or 4 root 2 over 3. These are all acceptable answers. Just simplified them. All right. So, review. We took the bounds off of our integral. I did use substitution like I would last chapter. And then I integrated. I added a plus c just for formality's sake. And then since I was done integrating, I only used u to help me integrate. I plugged in x cubed plus 1, which is what u equaled. And then I did f of b minus f of a with the bounds from earlier. And I got my answer. So method 2, u is going to be the exact same. So u is going to be x cubed plus 1, and du is still going to be 3x squared. That doesn't change. But now I need to find what my new bounds are. So I'm going to keep the bounds on. And let's see. So like u of 1 is going to equal 1 cubed plus 1. That equals 2. So we're going to have a 2 up top. And then u of negative 1 is going to equal negative 1 cubed plus 1, which equals 0. All right? And we can kind of take this little one step further and call this like u equals 2 and u equals 0. Because the whole time, when we first were starting, this was actually x equals 1 and x equals negative 1. All right, so now I've rewritten my bounds in terms of u, and I now want to rewrite my integral in terms of u. So it's going to look the same as above. So square root of u du. And we know that that's going to be 2/3 u to the 3/2. So now I don't need to plug in x anymore. I've already kind of did that once earlier by doing it already here and changing my bounds. So now I just need to plug in 2 in for u and 0 into u and use the fundamental theorem of calculus. So I'll get 2/3 to the 3/2 minus 0, because anything times 0 is 0. And that gives us to the same exact place as before. And if that was a little confusing, we're going to do a lot of these, so don't worry about it. All right, so then let's do another example. This one is in your textbook. It's problem 5.6.31. And it's the integral from 2 to 4 of dx over x ln of x, that quantity squared. So I'm actually only going to do method 2 because that's kind of the extra step of changing the bounds. And you are welcome to try method 1 on your own, but taking off the bounds and putting an x just kind of like we would last section. All right. So I'm going to rewrite my integral to make sure that we have, x equals 2, x equals 4, 1 over x ln of x squared dx. So if we were in class, I would ask you guys to choose u, and then we would work through and discuss what kind of u we would choose. You're welcome to pause now and try that. But I see that I have a 1 over x right here, and I know that's the derivative of ln of x. So I'm going to try u equals ln of x, and du is going to be 1 over x times dx, and we're just going to see how that goes, okay? So equal, so if I wanted to write this as 1 over x times 1 over ln of x squared dx. So there's du, and u is right in here. So u, du, du. So it's going to be 1 over u squared times du, right? Yeah. But I still haven't changed my bounds. There's still x's. So the whole point of u substitution is to make my integral in terms of u, including the bounds, right? That's why we change them. So I'm going to go step to the side. So when x equals 4, it's another way to write it, then u equals ln of 4. When x equals 2, u equals ln of 2. Right, because I defined u to be ln of x. So this is equal to ln of 2, ln of 4, and then I'm also going to take another step in 1 and make that u to the -2, just to help me with my integration. All right? I hope that wasn't too confusing. And now we are going to integrate. So we're going to have u to -2 plus 1 is -1 divided by -1. And I'm going to evaluate that at ln of 2 to ln of 4. All right, so that gives me -1 over ln of 4 minus -1 over ln of 2. And I think we can simplify this a little farther to be -1 over ln of, a little too many steps. 4 is 2 squared. So plus 1 over ln of 2. I'm just simplifying right here. You can totally stop here or even stop here. Beautiful. And this was just some combining of fractions. You don't necessarily have to get all the way to here. Both of these answers right here are perfectly fine. And this can even be a 4 down here. Whoops. Okay. So that's where we changed the bounds. And we never went back to x's ever. Okay? So let's do another one. And I think I might have enough space to do both methods. Let's try it. Alrighty. So this is also one of my favorite problems. So let's just look at u before we even decide which method we want. So I have e to the 2x here and x squared. Sorry, e to the x. So if I choose u to be e to the 2x, du would be 2e to the 2x, which I don't have. I only have e to the x. So let's rewrite our integral to look like someone's derivative that I know. 0 ln square root of 3. So I'm going to write it as 1 over 1 plus e to the x squared times e to the x dx. All right, so I just rewrote the integral. I did nothing with u. I just rewrote it being like, I know this looks like somebody's derivative, but I'm not 100% sure. So I know that arctan's derivative arctan of u, that derivative is 1 over 1 plus u squared times the derivative of u, right? So now I know that I can use something similar to this to help me choose u. I know you were thinking, like, how am I supposed to do that on my own? This is so difficult. This is what I mean by u substitution takes some practice, and then this is why I wanted to show you these types of problems. All right. So this makes me want to choose u to equal e to the x. Let's do method 1 for this one so that we can, because we're not too sure about our u. Method 1 really helps if I'm not really sure about my u. I can take the derivative later on before plugging in for the fundamental theorem, and that'll help out. All right, so if u is e to the x, then du is e to the x dx. When you choose u to be e to the x, you have to be careful. I'm not going to want to put du here, and I'm not going to want to choose u here, right? I want to do something like this. Okay? So we are going to take off our bounds. By bounds. So this is now going to be 1 over 1 plus u squared du. And I know that that is going to be arctan of u, and then I'm not going to add a plus c, which is then I'm going to plug in again, get rid of my u's because I only need them for integration, so I'm going to have arctan of e to the x. Okay? Now I'm like, ooh, not really sure about if that was right. Okay, well, let's take the derivative of this. Okay, well, I know that arctan's derivative is 1 over 1 plus something squared. Something being the inside, so 1 over 1 plus e to the x squared, so that was the derivative of the outside with the inside still the same, times the derivative of the inside. Well, then I can rewrite that, and I get e to the x over 1 plus e to the 2x. That matches where I started. Perfect. That means I did my choosing u right and taking the antiderivative right, and I got to where I needed to go. So good. Now I can plug in my bounds, ln of 3 and 0. So I'm going to take arctan of e to the x from 0 to ln of the square root of 3. All right, so that's going to equal arctan of e to the ln square root of 3 minus arctan of e to the 0. Well, e to the ln of square root of 3, that's just going to be the square root of 3. So arctan square root of 3 minus arctan of e to the 0. Anything to the 0 power is just 1. All right. So arctan square root of 3. Who can give me a square root of 3 if I divide its sine divided by cosine? Did you choose pi over 3? Good. So it's pi over 3. And arctan of 1, so whose sine and cosine are the same, is going to give me pi over 4. Okay? And you can just leave it right like this. That would be totally fine. And then you could take it one step further if you wanted to, and I think you get pi over 12. Let me check the back of the book because this is an odd number. Heck yeah, pi over 12. All right, so you could have left it as pi over 3 minus pi over 4, it's totally fine. But pi over 12 is just as unacceptable as an answer. All right, so if you want to try method 2 for this one, let's just set up that integral with the new bounds, and then you can work through it. You'll get the same like this, just the bounds will be a little different, and I bet you totally can work through that. So let's remember that u is, what is it, e to the x? So that means when x is 0, u is e to the 0, which is 1. And when x is ln square root of 3, u equals e to the ln square root of 3, which gives me, those cancel out, the square root of 3. So now I would work through this integral, but instead of going from 0 to ln of square root of 3, I'm going to go from 1 to root 3 of 1 over 1 plus u squared du. And then you would get to the same point. You would probably get to here instead of this line right above it. All right? So try that on your own and let me know if you need more help. All right? So that is the end of u substitution of definite integrals. Definitely do a lot of practice on that. Watch Bailey's video if you're still a little homework is there to help as well. Don't forget to do your homework. And yeah, all right. So now we're gonna move on to like a fun fact about definite integrals. So theorem 5.6.2. Well, first now we're on to definite integrals of symmetric functions, right? A function can either be even or odd or neither. So if f is even, so that means that f of a equals f of negative a. What do you think about the antiderivative? So if I do the integral of f from negative a to a, we're actually going to get 2 times the integral from 0 to a of f of x dx. All right, and if f is odd, meaning that f of a equals negative f of negative a, then if I take the integral from negative a to a of f of x dx, well, that's just going to equal 0. They're going to cancel out. That might sound a little weird, but you can think about it as using these pictures. Either side or across 0, if it's even, they're going to add together. So that's how we get the 2 right there. If it's odd, the other side is going to cancel it out, which gives us 0. So let's look at the picture. Sine of x is odd. So if we look at negative pi to pi, that red area is the same value as the green, just negative. So when I add these together, I'm going to get like area minus the same area. That gives me 0. And if you want, I can even show you, because sine from negative pi to pi dx, well, that's going to equal negative cosine of x dx from negative pi to pi. So negative cosine of pi plus cosine of negative pi minus a negative is adding. That's going to equal negative 1 plus 1. Well, that equals 0. Okay? X squared is kind of your typical even function. Remember, anything x to any even number is an even number, and x is an even function. X to any odd number is odd. So x cubed is another odd function that you could have played with for this example. This area right here from 0 to 2 is the same area from negative 2 to 0. So if I do the integral from negative 2 to 2 of x squared dx, that's going to give me x cubed divided by 3 from negative 2 to 2. which is 8/3 minus a negative 8/3. So we're going to add those together, and I get 16/3. Well, now what if I do 2 times 0 to 2, x squared dx? Well, that's still going to be 2 times x to the 3 over 3 from 0 to 2. And that's going to give me 2 times 8/3. No. I don't know what page this is on. Return? Oh, okay. We're only on page 5? Oh, God. Okay. I left a lot of spaces for doing some future verbs. Stop. Okay. So, where are we? 2 times 8 divided by 3 minus 0. That also equals 16/3. So that's really cool. Really helpful. Again, kind of with the speed of doing these. So during quizzes and exams, it might help you out. And later in math, it's really, really useful to know these properties. All right. So now we're moving on to a bigger idea, and that's the area between curves. So I spent a lot of time making this beautiful drawing. I have the area between f of x and g of x. I don't really know how to find those, though. I know that if I take the integral of f of x dx, that's going to give me this area down here. And I want to include this. Oh, I don't want to include this little bit. I definitely want to include this, but I don't want to include this. Well, if I go over and I look at it, if I just take the integral of g of x dx, that's going to take the area from g of x all the way up to the x-axis. So it's going to take up the area in between f here, which I want. But again, I don't want this little area. And I don't want this area. So if each of these integrals gives me the area between that function and the x-axis, how can I find the area in between them? So if we scroll up, we have our definition that says if f and g are continuous with f of x always being greater than or equal to g of x throughout AB, which we have in this picture up here. F, that line always lies above g. Then the area of the region between the curves f of x and g of x from A to B is, to that area, we're going to say A equals the integral from A to B of f of x minus g of x dx. So we're going to subtract the higher one from the lower one. All right? So there's a lot of steps when it comes to finding the area between two curves, or that the area enclosed between two curves. Sometimes we're given a few of them, and sometimes we're not. So finding A and B, sometimes we aren't given it, sometimes we are, or sometimes we're not told which function's on top. And sometimes one function isn't always on top, and it switches. All right? And we'll see lots of I chose a variety of problems, so you'll be able to see that. Okay? So our first example is to find the area of the region bounded above by the curve y equals 2e to the negative x plus x. So that tells me right there that that one's on top, and below by the curve y equals e to the x divided by 2. That gives me my bottom function, and from 0 to 1. So we're already given our bounds, 0 and 1, so we don't need to find them. We're also already given that e to the 2e to the negative x plus x is our top function. So I kind of just need to plug and chug into this equation up here and then work my integration magic, and we should be good. So that means that the area between them is going to be 0 to 1, my top function minus bottom function. That's another way we can write it. A to B, top minus bottom. So who's my top function? 2e to the negative x plus 1, no, plus x, minus e to the x over 2. When you're doing the subtraction right here, make sure you're subtracting the whole entire function so that you don't forget to distribute that negative to other terms. That'll mess up your whole problem. I'm warning you now. Okay, so I usually like to distribute my negative first and also combine any terms if need be. Oops. I don't think I can combine any terms right there, so I think we're pretty good. All right. So this is going to be negative 2e to the negative x plus x squared over 2 minus e to the x over 2. All right. This negative right here comes from this negative in front of the x right here. We learned a quick integration rule, or antiderivative rule, that said e to the kx is, the antiderivative of that is e to the kx divided by k, but dividing by -1 is the same as multiplying by -1. So that's why that negative is in front of that too. All right. And we're going to evaluate this from 0 to 1. So this is going to equal negative 2 e to the -1 plus 1/2 minus e to the 1 over 2 minus negative 2 e to the 0 plus 0 minus e to the 0 over 2. And e to the 0 we just talked about, this is just a 1, 1. So we're going to simplify this to negative 2 over e plus 1/2 minus e over 2, whoops, minus negative 2 minus 1/2. It's going to be minus, we'll say 2.5. And then that makes that a positive, so 1/2 plus 2/2 is 3. So we'll get 3 minus 2 over e minus e over 2. All right. You could have just stopped here if you wanted to, or here. I just like to simplify it as much as possible. And if you were curious, this is about 0.9051. Yeah, 1. All right. So other times we're not going to be so lucky to be given who's on top and our bounds. All right. So the next one is to find the area enclosed by y equals 2 minus x squared. And I know that that is a parabola. And y equals negative x. And I know that that's a line. I know that because polynomials with x squared as the highest power, those are going to be polynomials. And x, the first power, is going to be a line. Okay? So I need to find the bounds of my integral. That's going to happen where those points intersect. Okay, so if I kind of draw like a rough sketch of what we're kind of looking at is like something like this. The area enclosed between the parabola and the line is this area right here. This is a really rough picture. All right. The area enclosed is not this other area. That's not enclosed in the parabola. Okay? So we need to find the bounds. So we need to set these two things equal to each other. So we're going to have 2 minus x squared equal to negative x. I'm going to add x over. So I get 2. I'm also going to actually, yeah. So I'm going to do x squared minus x minus 2. So I actually moved everything onto the other side. Equals 0. I did that for the sole purpose of that x squared would be positive because that helps me factor. All right, so this is going to be x plus or minus something, x plus or minus something equal to 0. Multiplies to negative 2 and adds to negative 1. So I think that's x plus 2 minus 1. Multiplies to negative 2, yeah. 2 minus 1. Nope, that doesn't work. Let's do minus 2 plus 1. Yes, that works. Okay, cool. So that means that x equals 1, sorry, negative 1, and x equals positive 2. All right, so those are our bounds. So now our integral is going to look something like negative 1 to 2, top minus bottom. But who's top, who's bottom? I don't know. How do we figure that out? Well, if I just plug in a number between negative 1 and 2, whatever gives me a larger number, that's going to be on top, right? Because top and bottom is deemed by the y values. So let's plug in 0. If you want to call these two things, they're both called y. It might help if you call them y1 and y2. So whoopsies. So y1 equals 2 minus 0, which just equals 2. And y2 equals negative 0, which that's just 0. So 2 is greater than 0, so y1 is on top. Yay! Since the only two places for the 2 points to intersect are the bounds, it means y1 is on top for that whole entire interval. All right? So now we're putting it all together. I have my bounds and I have top. That leaves my other function to be bottom. So we're going from negative, come on, pen. There we go, negative 1 to 2. What's my top function? 2 minus x squared. 2 minus x squared minus negative x dx. All right, so negative 1 to 2. 2 minus x squared plus x dx, and then we're going to integrate. So that's going to give me 2x minus x cubed over 3 plus x squared over 2, and we're going to evaluate that from negative 1 to 2. Don't forget that constants, when you integrate them, become coefficients, right? So that's where we get a 2x from 2, okay? Constants don't go away when we're doing the antiderivative. They gain a partner. All right, so let's plug in 2. So 2 times 2 minus 2 cubed over 3. Let's take this down to the next line. Plus 2 squared over 2 minus, please, 2 negative 1 minus negative 1 cubed over 3 plus negative 1 squared over 2. Okay, so this is going to be 4 minus 8/3 plus 4 divided by 2. 2 squared divided by 2 is just 2 minus negative 2. Negative 1 cubed is negative 1, so this is negative 1/3, but there's a minus right there. So this is plus 1/3. Oh, excuse me. Plus 1/2. Which is the same as 4 plus 2 is 6 minus 8/3 plus 2, gotta distribute my negative, minus 1/3 minus 1/2. So 6 plus 2 minus 1/2 is going to be 7.5, and then negative 8/3 minus 3 is going to give me minus 9/3, which is just 3. So this is going to give me 4.5, which is also 9/2. This one I kind of expect, I mean, either of these answers is beautiful. Kind of expect a little bit more simplification with these, since this one isn't too difficult, since it's all like 1/3 and 1/2 and whole numbers. So I would expect for you all to simplify this one down. Okay, so that was pretty nice. We weren't given our bounds, but we obviously had to be given 2 functions. So we found our bounds by setting the functions equal to each other, and then we tested a number in between to see who was on top, and then we put it all together. So now let's look at another type of problem. We're actually going to revisit this and do this same problem a different way later on too. So we're going to find the area of the region in the first quadrant. So the first quadrant is when x and y are both positive. That is bounded above by y equals the square root of x and below by y equals x minus 2. So these are pretty easy curves that we know how to draw them. I know how to draw y equal to x minus 2, and I know how to draw the square root of x. And from that drawing, I can see that there's some interesting things. So there's also the area of the region in the first quadrant. So we kind of also are given like a hidden third line. I'm not gonna make that red. What have I not used? Teal. Purple. So I have this invisible other line, which is y equal to 0, right? So, or is that x equal to 0? It's the x-axis. Yeah, it's when y equals 0. So what's happening here is, since I only need the first quadrant, this area down here isn't needed at all. I don't need to calculate it. So I kind of need to make 2 different integrals, right? Because x minus 2 isn't really involved at all until whatever that point is, until it hits the x-axis. So I need to make an integral for area 1 and area 2, okay? So we only want the area in the first quadrant. Maybe if I spelled area right. There we go. All right. I'm actually going to erase this because I want this space. I think it gave us a lot of space though. Holy crap, I did. Okay. So let's do area 1. To do that, my lower bound is the axis. Well, that's kind of already inherently involved in the integral, right? It's only going to take the area down to the axis. So, right, because there's always kind of like a, if I do f of x minus 0 in an integral, well, that's the same as like f of x, right? So I need to find out at what point is x minus 2 above the x-axis, all right? And then when we do area 2, we can find out when they're equal. All right, so when x equals 2, that's this little point right here. So area 1, my bounds are going to be when x equals 0 and when x equals 2. For area 1, I also know that the square root of x is going to be greater than 0. And it always is greater than 0, except for at 0. All right. So I can write it as like the square root of 0 minus 0, which is the same. Oopsies, I forgot my dx. There we go. So this is going to be x to the 3/2 times 2/3 divided from 2 to 0, excuse me. I know what you might be thinking of, how am I supposed to know how to do this? It's because these curves are simple enough that you can just draw these pictures. When the textbook gives us this sketch, but I would have the confidence that you all would be able to draw x minus 2 and the square root of x. All right, and know what the first quadrant is. We reviewed that when we first reviewed trig functions. All right, so now I'm going to plug this in. I plug in 2 and I get 2 times root 2 over 3 minus 0. So this equals 4 root 2 over 3. So that's what this area 1 equals. We'll say area 1. Area 2 now involves our two original functions, square root of x and x minus 2. I know that my lower bound is x equals 2. What's my upper bound? It says 4, ignore that. We're going to figure it out. So I'm going to set the square root of x equal to x minus 2. And you're like, I don't know how to like solve anything with a square root. Like, ooh. Well, what if we squared both sides? So square, square. I'm in the first quadrant, so I know x is always going to be positive anyway, so it's totally fine that I'm doing this. So I'm going to get that x equals, let's FOIL those out, x squared minus 4x plus 4. So if I subtract that x over, I'll get x squared minus 5x plus 4. And so x, things that multiply to 4 and add to -5. Well, that is -4, -1. Oops, not -4 again. -1. So -1 times -4 is 4. -1 plus -4 is -5. Okay, cool. So that gives us x equals 1 and x equals 4. Well, I know my lower bound is 2, so I can't choose x equals 1. That doesn't work. So I know I'm going to go up to x equals 4. And we can also double check this, because the square root of 4 and 4 minus 2, well, square root of 4 is 2, 4 minus 2 is 2. So just to double check that that does make sense, that's where those two cross. All right, so I now have the integral from my lower bound that I already knew and to 4, which I just found. And now I need to find who's top and bottom. So I don't recommend plugging in your endpoints, because that's usually where they're going to equal each other. So even in this case, x equals 2 is not where they meet, just to kind of save yourself a little bit. You can do a point in between 2 and 4, and I would choose 3. So y1 we're going to call the square root of x, and y2 we're going to call x minus 2, and we're going to plug in x equals 3 just to see who's on top from 2 to 4. So I get that y1 equals the square root of 3, and I know that y2 is going to be 3 minus 2, which equals 1. Well, I don't know what the square root of 3 is, but I know that the square root of 1 is 1 and the square root of 4 is 2, so square root of 3 has to be between 1 and 2, so greater than 1. So that means that y2 is going to be bigger than, y1 is going to be on top. y1 is wahoo! Okay, cool. So that means that my last integral for area 2 is going to be from 2 to 4 square root of x minus x minus 2. Remember to put that in parentheses because you need to distribute that negative. All right, and I can then rewrite my integral to distribute that negative. So square root of x minus x plus 2 dx. So this is going to equal x to the 3/2 times 3/2 reciprocal, which is 2/3, minus x squared divided by 2, plus constant's antiderivative is that the constant becomes a coefficient in front of x. So I'm going to evaluate this from 2 to 4. All right. So let's plug in 4, 2, 4 cubed, oopsies, 4 to 3/2 for 3 minus 4 squared over 2 plus 2 times 4 minus 2 times 2 to the 3/2 over 3 minus 2 squared over 2 plus 2 times, oops, not 2 times 4, 2 times 2. So then what I like to do when calculating something to the 3/2 is if it's a perfect square, like 4, 9, the 16, I forgot the, no, yes, 16. I like to take the square root and then cube it. So this is gonna be like 2 times, the square root of 4 is 2. So that'll give me 2 cubed, which is 8. Cubing 4 and then taking the square root of that is difficult, so I don't recommend doing that. 4 squared is 16, divided by 2 is 8, plus 8, minus, I know that this is 4 square root of 2 over 3, minus 2 squared over 2 is just 4, plus 4, it's crazy, those things cancel out. So then we get cancel, 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 cancel. What's 2 times 8? 16. 16 thirds minus 4 root 2 over 3. I'm happy with that. Let me make sure I didn't miss anything. Oh, I did. There it is. This is a 2. And that is plus 4. Okay, there we go. So that is minus 2. Okay. We did it. So that is, what, 10 thirds minus 4 root 2 over 2. Okay, cool. We're not done yet, remember? That was just the area of the second part, right? So I need to combine, my total area is going to be A1 plus A2. A1, we can scroll up, 4 root 2 over 3. Plus 10 thirds minus 4 root 2 over 3. So those actually cancel out, and I just get 10 thirds, which is kind of why I went back and checked on that -2, because I was Confucius. All right. So this one was a pretty lengthy one. Absolutely. If you can, using all the knowledge that we've kind of so far taken with learning different types of equations, I would definitely attempt to sketch, the best of your knowledge, the graphs. So you know how to draw a line and you know how to draw a simple curve like x squared or square root of x. All right. So these two I don't expect you to know how to draw. Excuse me. This one actually does come with a picture in the textbook, but let's just assume that we don't have that. So let's assume that I know nothing else about other than just I'm given y1 equals negative x squared plus 3 and y2 equals 2x cubed minus x minus 5. Alrighty. So we're going to set them equal to each other so that we can find the bounds. So find bounds by y1 equals y2. All right. So we set those two things equal to each other. So I called y1 negative x squared plus 3x equal to 2x cubed minus x squared minus 5x. All right. So then if I add x squared to the other side, I'll get 2x cubed. Those two cancel out. And I will get, no. Yes, they do cancel out. There's something, did I write this right? Yeah, okay. Minus 8x, right? That equals 0. Okay, cool. So then 0 equals, each one of these terms has an x in it. So I get 2x. Ooh, I could actually pull it at 2x. Let's do that. 2x, and it's gonna be x squared minus 4. Aha, that's what I wanted. Okay, cool. So that means that x will equal 0, and that x squared minus 4 equals 0. And that's the same as x minus 2, x plus 2, right? So now I also know that other than x equals 0, x will also equal 2, and x will equal -2. So now my graphs are intersecting at 3 points. So I'm going to have, to find my total area, I'm going to have some integral that looks like -2 to 0, whatever that hoo-ha is in the middle, plus 0 to 2. Maybe. They could just accidentally touch and move on, but I need to at least check, right? I need to make sure in each one of these integrals, I need to check who's the top and who is the top between 0 and 2. All right, so let's do area 1 plus area 2 again, right? So area 1 will be the integral from -2 to 0. So area 1, which is going to be -2 to 0. And then area 2 will be 0 to 2. Okay? So we've split those guys into the two bounds. So now we need to see who's top and who's bottom. A fun number to plug in between -2 and 0 is -1. So y1 at, not 1, -1. That's going to be -1 squared plus 3 times -1. So that'll be -1 minus 3, which is -4. So y2 at -1 will be 2 -1 cubed minus -1 squared minus 5 times -1. Okay, -1 cubed is -1, so it'll be -2. Minus 1, -1 squared is just 1, so -1 minus a -5 will be a +5. So -2 minus 1 gives me -3 plus 5 will give me a +2. Right? So y2 is on top. And -2 to 0 on that little interval. Okay? So this interval is going to be -2 to 0. What next? Top minus bottom, right? So top is y2, where y2 is 2x cubed minus x squared minus 5x minus the entirety of y1, which is x squared plus 3x. And that whole body is multiplied by dx, right? So equals negative 2 to 0. Let's see. That's going to be 2x cubed minus, so if I distribute this negative, that's going to be a plus, and that's going to be a minus. So plus x squared minus x squared just goes away. So boom, boom. And minus 5x minus 3x, so I'll get minus 8x. Not too bad. dx. All right. So then we'll take the antiderivative. I get x to the 4th. Keep my 2, and then I'm going to divide by 4 minus 8x squared divided by 2 from negative 2 to 0. All right. What I like to do is kind of simplify as I'm plugging in numbers. So I know when I'm plugging in 0 here, everything's just going to be 0, because that's going to be 0 minus 0. Minus, this is going to be negative 2 to the 4th. 2 divided by 4 is just a 2 on the bottom. Minus 8 divided by 2 is 4, so this is going to be 4. Negative 2 squared. Don't forget this negative out front. It'll ruin your whole answer if you forget about it. So this is going to be negative 2 to the 4th is going to be 16 divided by 2, so 8 minus 2 squared is 4. 4 times 4 is 16. So this is going to equal negative 8, which is just 8. Great. That's a simple enough number that I'm confident in it. All right, so that was area 1. Now we're moving on to area 2. We cannot just assume that since they intersected at 0, that they switched top and bottom. So we still need to check. So now let's just plug in 1. So y1 equals negative 1 squared plus 3 times 1. So that's negative 1 plus 3, which is 2. And y2 at 1 is going to be 2 times 1 cubed minus 1 squared minus 5 times 1. So that is 2 minus 1 minus 5. 2 minus 1, which is going to be 1, minus 5 is negative 4. So now y1 is on top. So they did switch top and bottom. All right, so that means we're going to have the integral from 0 to 2, y1 minus y2. So I'm going to have negative x squared plus 3x minus 2x cubed minus x squared minus 5x. And that whole thing times dx. Going to simplify before I integrate to save my life. So negative 2x cubed, negative x squared minus a negative x squared. Those two just cancel out again. And then 3x plus 5x, so plus 8x dx. You could have also seen from when we did the area of part 1 that this is just the negative version, right? y2 minus y1 and vice versa, just kind of like multiplying by negative 1. All right, so we can integrate. So I'll get 2x to the 4th, negative 2x to the 4th divided by 4 plus 8x squared over 2, and evaluating that from 0 to 2. So this is going to equal -2 to the 4th, or actually we can simplify that. 2 to the 4th over 2 minus 4, 2 squared, minus 0, right? So this is going to be -8 plus, oh no, not plus. Oh wait, that's a plus. Yeah, plus. Okay, plus 16, right? And that also equals 8. That was fun. All right, then we can add those both together. And I get 8 plus 8, which equals a whopping total of 16. All right. So when we get that our function intersects 3 times, means we're probably going to have at most 2 different integrals that we need to deal with. Okay? So let's scroll down. So now integration with respect to y. This part's going to be the last part, and it's also going to be a little shorter just because it's not as common as kind of what we've been doing, but it's a really useful trick. Not trick, method. So how do we find the area between the yellow line and the green line from C to D, where C to D are y values? Well, if I was kind of looking at the x values, I would have trouble trying to find the area between here and here because those are the same value. If I'm trying to find like this, like Riemann sum, that's like not gonna really work. So these, we usually have y equals something, some version of manipulated with x. Well, these functions are usually described using y instead of x. All right, so I flip to the right page in my textbook. Excuse me. Our updated formula is now going to be, instead of a going, the area being going from A to B, we're going to go from C to D, and that's going to be f of y minus g of y dy, where f of y is the function on the right minus g of y the function on the left. So we can even write that again. C to D, our right function, so we'll call that capital R out of x, y, minus our left function. All right. So this is actually really useful, kind of on a problem that was a little tricky from earlier. So let's revisit y equals the square root of x and y equals 2 minus x in the first quadrant. We are going to rewrite y equals the square root of x in terms of y. So basically I'm going to solve for x. So I square both sides and I get x equal to y squared. And for y equals x minus 2, I want to get it in the version of x equals something. So x equals y plus 2. I just added 2 to both sides. All right. So I know when I was doing this problem earlier, I had 2 integrals to find my area, right? I had an integral from 0 to 2 plus another integral from 2 to 4. Those are all x values, remember? So my area went from 0 in the x to 0 in the y. Sorry, 0 to 4 in the x. Ugh. So to help me find that again, oh no. Okay, whew, that was scary. I want to find my bounds in terms of y. And I can do that a few ways. I can set these guys equal to each other again, or since I've already done this problem with this point equaling them, I can plug that into either one for x, and I can solve for y. But let's do it the other way and set them equal to each other. So now we're going to have x1 equal to y squared, and x2 equal to y plus 2. So we're going to set these equal to each other, so I get y squared equal to y plus 2, which is the same as y squared minus y minus 2 equal to 0. And I can factor that to being y minus 1 and y plus 2. Negative 1 and 2 multiplied to negative 2, negative 1. Nope, let's switch those. Let's do plus 1, and let's do y minus 2. Yes, that works. Okay, because then I'll get a negative y. Awesome. So that gives me y equals negative 1 and y equals 2. Well, I can't go down to y equals negative 1, right? I'm in the first quadrant. Y has to be positive. So I'm actually going to start at 0, because that's the x-axis, right? That's still kind of involved. We still have to talk about the first quadrant. So we can say that our bounds are y equals 0 from the first quadrant information, and y equals 2, which is where x1 and x2, let's say, equal, intersect. All right, so now what? Found our bounds. We're not going to find who's top and bottom. We need to find who's left and right. And I know what you're going to be saying. Oh, is it like the same? Maybe, but when you are switching from y to x, you're kind of rotating it, so it's still best to see who is left and right. The higher number is still going to go on top. So I'm going from 0 to 2, so let's plug in y equals 1. So x1 is y squared, so that's just going to be 1 squared, and that equals 1. x2 equals y plus 2, so that's 1 plus 2, and that equals 3. So x2 is on the right. All right. So remember, when we're talking about things in terms of y, we want to do right minus left. So putting in my bounds from 0 to 2, right minus left, so that's going to be x2 minus x1. Remember, we're in y, so dy. x2 is y plus 2 minus y squared dy. All right, and we can integrate, so that's going to be y squared over 2 plus 2y minus y cubed over 3, evaluated from 0 to 2. All right, so we're going to plug and chug, so we're going to put in 2 squared over 2 plus 2 times 2 minus 2 cubed over 3 minus, that's, if I plug in 0, I'm going to get a big 0 back out. All right. So 2 squared divided by 2, it's 4 divided by 2, which is just 2, plus 4 minus 8/3. So what's that gonna be? Six minus 8/3, which I just want to double check that it's 10/3, which is what we got earlier. 3 times 6 is 36 minus 8. Nope. That is not 3 times 6. 18 minus 8. Yeah. Perfect, 10/3, which is what we got earlier. So even though we kind of switched who we were integrating with respect to, we still get the same answer, which is pretty great. Also, I only needed 1 integral this time, which is a lot easier than that 2 integral, seeing who's on top when, and kind of need to knowing a lot more about it. So if you're not ever indicated to try it with y, sometimes it's easier, sometimes it's not. Sometimes it helps, and it all takes about practice. So that's kind of what the homework here is for, is to help you practice. Also, hopefully to help you with your grades, since you do get unlimited attempts on all the problems. All right, so let me know if you guys have any questions, and that should end probably the longest lecture that we have to date. All right, see you guys next time.